Continue with section 10.4. Okay, from the previous lecture, we learned that if C is the field in here, piecewise smooth, positively oriented, closed and simple, then we can apply the Green theorem to compute circulation in R2. Circulation in R2. Okay, so the Green theorem again is this. F dot dr. It is the same as that. You can break it up into component wise. Pdx plus qdy, and this is equal to the big circulation is going to be the sum of all the smaller circulation over that region D formed by the curve C. And this one is the Qx minus Py dA. Yeah, it's the Green theorem here. Now, if Qx minus Py equal 1, then we can figure out the area of the region D. Notice that if Qx minus Py equal 1, then double integral over D 1 dA is area of region D. So when does this happen? Next is the when. When does the Qx minus Py equal 1? Pxy equal what? Qxy equal what? Well, you can just quickly see this, right? You want Qx minus Py to be 1, right? So that means Qxy has to be x, and this has to be 0. So that's one case. Pxy equal to Qxy equal to. The other one is that Qxy is going to be 0, and then Pxy, where we want 1, so this has to be a negative y. Because when we take the partial derivative with respect to y, get negative 1. Minus 1 is going to give us 1. And then another case is the Pxy and Qxy. Well, if we can get each one of them to be a half, then you should get 1. So For the pxy, because we have a negative here, it's going to be a negative half y and this is half x. Any of these line integral will give you the area of region D. Find the area enclosed by the ellipse. X squared over a squared plus y squared over b squared equal 1. There's the ellipse right here. We can figure out the area using, of course, the green theorem. This is the green theorem here. Well, in order to do this thing here, you got to parameterize the ellipse. Which formula you want to pick here? It doesn't matter which one. You can try the other one. I just pick x dy here because it looks pretty simple. So yeah, okay. X equal a, negative a, b minus b. Okay, so it looks like area is the double integral over the region D of 1 dA. Fortunately, from the green theorem, we have a we have this to be either one of them, doesn't matter which one. Line integral over the curve C, x dy. Well, when we do the line integral over the curve C here, this is the curve C. This C right here. Well, you can do this. You can have the arrow go this way so it match up with the green theorem. Right? And then from here, what do we do here? We got to parameterize C. In order to do the line integral, you got to parameterize the curve C. So how do we parameterize C here? X equal to something and y is equal to something, so that x squared over a squared plus y squared over b squared has to be 1. The parameterization is pretty similar to how you parameterize the circle. So it would be a cosine t, b sine t, 0 less than equal t, less than equal to 2 pi, because we go the entire cycle. Yeah. Okay, so parameterize this, and we're gonna have a 0 to 2 pi. X is a cosine t, and then dy is the, make sure that you do the dy here. Huh? B cosine t dt. So that's your dy. Huh? b cosine t dt. Yeah. Okay, so what do we have here? We have a AB integral 0 to 2 pi cosine square t dt. And most of you already did this thing in math. One B. Well, you integrate cosine square t going 0 to 2 pi. This would be anybody AB pi. Okay. Figure out which method to use. A. Find the work done by the force field. Okay, so here's the vector field. Z, X, Y in moving a particle from three zero zero to 0.2 3 along the curve C. Along this one. Three cosine t, t, 3 sine t. So that's the first one. Okay, so here comes the second one. I'll give you some room here. Find the work done by the force field. For x3 y square minus 2 x y3 2x to the 4y minus 3x square y square plus 4y3 in moving a particle from t equals 0 to t equals 1 along RT is t plus sine pi t 2t plus cosine pi t So here comes C. Find the work done by the force field. In moving, there's the force field here. Y cosine x minus xy sine x, xy plus x cosine x in moving particle. From zero zero to 04 to 20 200. This one gonna be the first one. So they just call it general line integral. Okay, I did this thing here. I'm gonna give you guys the answer in case you want to do this and get some practice. Negative 3 pi over 4. You do it, you're gonna get negative 3 pi over 4. Okay, in the second one, conservative vector field. Okay, do the work. The answer here is amazingly 0. Okay, last one. The green theorem would be a better approach here rather than the general integral. So green theorem is the better approach. So the answer is negative 16/3. General line integral, then you got to do 3 line integral. You need 3 integral. Integral C1 f dot dr, integral C2 f dot dr, integral C3 f dot dr. C1, C2, C3. Most of you see you just go from one point to another. So I'm gonna go over the setup. Okay, let's set this thing up here. Okay, so we are moving from 0 0 to 1 4. I mean 0 4, and then 2 2 0. and back to 0, 0. As you can see, there's the curve C here. C is the clockwise. C traverse clockwise. Now, we cannot use the green theorem. We can only use it for counterclockwise. So we got to do a negative C. Negative C traverse counterclockwise. Or positive orientation. Okay. What does this mean? It means that when we do the work, there is circulation here. Work would be C, right? F dot dr. This one is gonna be a negative because negative C. So you put a negative here. You integrate over negative C instead of C, and it's gonna be a P dx Q dy. So okay. Next step is, well, everybody see the region D here. Did you see it? And use it. Region D. DA here is, it doesn't matter because there's just a straight line here. You can do dx dy or dy dx. Now, a lot of us learn how to get the equation of the line. So this straight line right here, we learn the equation is y is equal mx plus b. So most of us stick to the slope as -2 and then the y-intercept as 4. We learned this one. So if we have this, it is better to do dy dx. Y go from 0 up to the line. And then x go from 0 to 2. Remember, that's the setup right here. Okay, so now, well, we see that C is closed and bounded, right? Traverse counterclockwise is negative C. We integrate with negative C, not C though. Negative C is closed and symbol. A symbol closed. Traverse counterclockwise. Yes, this was smooth that information. Three information. So once we know this about C, right, then we can use the green theorem, right? Okay, to use green theorem. Okay, so the green theorem is going to be a negative, right? You still have the negative here. It's going to be double integral over the region D, right? And well, partial derivative with respect to x up x y plus x cosine x minus partial derivative with respect to y cosine x minus x y sine x. And dA, oh my god, I got to figure it. And I should have write smaller here. Yeah, okay. Negative, well, the integral, right? Everyone knows how to set up 0 to 2, 0 to minus 2x plus 4. And when you do this thing here, it will cancel out nicely. You're just gonna have a y because the dA is dy dx. So I'm gonna leave this thing to you guys. And of course, the answer is it's gonna be a negative number.